These are the notes for Algebra 2, Section 7.3. We're looking at functions involving e. Now, you might be wondering just what e is, and that's understandable. You've never seen it before. E is what's called the natural base e. It's an irrational number. Now, we've seen other irrational numbers before. An irrational number is a number that can't be written as a fraction. And some examples that we might know, we know pi. Pi is an irrational number. Pi is equal to about 3.14159, etc., etc., etc. We also know I. I is an irrational number. It's equal to the square root of -1. And e is also an irrational number, right? Just like these other guys. The way we define e, though, is a little bit different. Now, we have this function here, the 1 plus 1 over n to the nth power. This is actually based on the compound interest formula because it's a very similar setup, right? 1 plus r over n to the nt. In this case, r and t would both be 1. There's no t here, and instead of r, we have 1. But n is n. It's in the same places. Now, as n approaches infinity, positive infinity, in other words, as n gets bigger and bigger and bigger and bigger and bigger, when n is 3, when n is 5, when n is 100, when n is 1,000,000, when n is 2,000,000, when n is 1,000,000,000. As n gets bigger and bigger and bigger and bigger in this function, e, the letter, gets closer and closer and closer to about 2.718. And it trails off, and numbers keep going forever. We could write 1,000,000 decimal places here off to the side, but we're going to stick with 2.718. Just like pi, we could keep going after 14159, I think it's 25 or 27, something. E is the same way. The decimals just keep going and going and going forever. So that is the definition of e. So when we're talking about e, we're talking about an irrational number that's about 2.718. Now, it has a lot of interesting properties. We'll be looking at some of them when we deal with logarithms, which is coming up soon. If you were to go into a calculus program, you would be dealing with e a lot because it shows up all over the place. We're just doing a very basic introduction of e, just so you can get a feel for how it works. We are going to use it in a compound interest formula. We'll see that later on. To start with, though, we want to do some of the basic stuff that we've been doing with other variables, but this time we're going to do it with e. For the most part, we can treat e as though it was x or y or any other variable. The fact that it actually has a value is nice, but we don't always need to worry about that. So for instance, all of our exponent properties work, and we're going to be using those exponent properties here. Right? For instance, if I multiply two terms, we know that I add the exponents. So if I have e to the 6th times e to the 3rd, that is e to the 6 plus 3, which is e to the 9th. Simple. That's that exponent rule that we've dealt with pretty extensively. We can keep going with all of our exponent rules if we want to. For instance, here we have 18e to the 6th over 2e to the 4th. 18 over 2 is 9. E to the 6th over e to the 4th is e to the 6 minus 4, because when we divide the terms, we subtract the exponents, which gives us 9e squared. Right? That exponent property that we're used to shows up with e. We deal with it the exact same way. Same thing here, raising a power to a power. Another property we've seen a lot. When we raise 4e to the 3x to the second power, we get 4 to the second power, and then e to the 3x times 2, because we multiply the exponents. Again, that exponent property that we've seen before. 4 squared is 16. E to the 3x times 2 is 6x. So e to the 6x. All right, so all of our exponent properties still work, and we need to remember those exponent properties. They're not going away. So we're going to get some practice with e this time instead of just x. All right, other things that we might need to do with e is to actually evaluate it. Now, of course, we're not going to be evaluating values of e by hand. We're going to be using the calculator. And fortunately for us, the calculator makes life easy when we're talking about e. So we want to find the value of e to the negative second. We go to our calculator. We have an e button. The e button is second ln. We have this ln button here. Second ln gives us e, and it gives us the exponent symbol. All right, so we have e to the something power. Now we have e to the negative second, so for the exponent we put negative second. And then we hit enter. And it gives us this long string of decimals. Pretty much every time we do one of these evaluations, we're going to get a long string of decimals. Doesn't matter. We're going to round it. And we'll round it to 3 decimal places. So e to the negative second is 0.135. We'll lop off everything after that. I think 3 decimal places is nice. We don't need to go with 4. That might be a few too many. 2 is probably a few too few. So e to the negative second is about 0.135. E to the 0.3, again, we do the same thing. We do second ln for e to the x, and we can plug in our exponent here. In this case, it's 0.3. We hit enter, and e to the 0.3 power is 1.39485, so on and so forth, which 3498 would round up to 0.35. So e to the 0.3 is 1.35. And that's the evaluation. Purely plugging stuff into the calculator and getting an answer. The last thing that we're going to really be concerning ourselves with e is a compound interest formula. We've seen compound interest formulas when we compound the interest daily or quarterly or monthly or yearly or something like that. But most of the time, interest is actually compounded continuously, as in over and over and over again, every second, every fraction of a second, constantly being accrued. So instead of having our compound interest formula that we would use if we're compounding the interest quarterly or monthly, if we're compounding the interest continuously, as in we're just always doing it every fraction of a second, then the amount in the account after t years is given by a different formula. And the formula that it's given by is P for principal, e to the RT. So we still have P, we still have R, we still have T. The value we're missing is N, right? That N, that number of times per year that interest is accrued, is not there because interest is continuously being compounded. So N isn't involved anymore. Instead, we have P times E to the RT. P, of course, is the principal, just like it was in the other compound interest formula. R is the interest rate. And of course we have to express R as a decimal because anytime we're dealing with percentages, we always have to use decimals. Now let's look at an example of how we would use this. Unsurprisingly, it's going to be very similar to when we did compound interest that was compounded any other span of time. We have P, we have R, and we have T. And we need to pull those values out and use the formula. So let's look at this. Now, we deposit $3,500 into an account that pays 4% annual interest compounded continuously. What's the balance after 1 year? So we have values. We have principal of $3,500. We have the annual percent interest expressed as a decimal is 0.04. And we have T, the amount of years it's in the bank, is 1. So let's get this done. Let's start by writing our formula. All right, our formula here is A equals PE to the RT power. And we're going to plug in P, R, and T. So here we are. A equals, change my color here, 3,500. P is 3,500 times E to the 0.04 times 1, R times T. And we can type this directly into the calculator, which will give us our value for A. So let's do that. We go to our calculators, main screen, mine just turned off, and we type it in. 3,500 times E, again we use second ln to get E to the exponent here. Our exponent is 0.04 times 1. Hit enter, and we're told that the amount is 3642.84, rounding it to the nearest cent. So 3642.84 is the amount of money that would be left in the account, or that would be in the account if the interest is accruing, it's not leaving, after 1 year if interest is compounded continuously at 4%.